again. Okay. All right. So Monday, 22nd, we are almost done with all the material that I wanted to cover. The two topics that are remaining are resonant circuits and AC power. Okay, resonant circuits and AC power. So let's see. My goal is to get through everything today and finish it up. And it should be doable. So let's get started. Believe we stopped here. Series resonance circuit, where I introduced the concept of a crossover network as a practical example. So just a brief recap. This chapter is about frequency response of electric circuits. Frequency response means we are, well, not means, but for frequency response, we use the impedance characteristics of inductors and capacitors because their response to the varying input frequency of any input signal depends on the, let me back up. The impedance or the reactance of a capacitor and inductor depends on the frequency of the input waveform or the input signal. For a capacitor, it is inversely proportional to the frequency. For an inductor, it's directly proportional to the frequency, right? So ZL is directly proportional to frequency, and ZC is inversely proportional to frequency. So we saw first order filters where you had a RL circuit and RC circuit, and then series resonances where we have an RLC circuit. So RLC means it has resistor, inductor, and capacitor. So this is also an example of a second order circuit or a second order filter. Okay, second order circuit or a second order filter because it has two energy storage elements. Two energy storage elements. So it requires a second order differential equation to solve for the voltages and currents. Hence, it is a second order circuit. And because we can use this as a filter, can function as a filter circuit, it is also known as a second order filter. Okay. So any questions so far? Okay. All right. So series resonance basically implies that it is a series circuit, meaning all components are connected in series. Okay. They are connected in series because there is no third component connected at any one of these nodes. The wires that are extending out, they are simply measurement terminals, meaning this is where we connect our output. Okay, so as far as the circuit is concerned, those wires, again, do not have any components. So as far as the circuit is concerned, the R, the L, and the C are all connected in series. Okay, hence it's a series connection. And then at a particular frequency, an electrical phenomena takes place, and that phenomenon is known as resonance. Hence the name, a series resonant circuit. Okay, series resonant circuit. If you take the output across the resistor, the incoming input signal for Vs, meaning if Vs has varying frequency components, it filters out, meaning it blocks the high and the low frequencies depending on the values of RL and C. And you have a certain band in the middle that is allowed to pass through, which you obtain across the resistor. So it functions as a band pass filter. If you take the output across the inductor, then you get the high frequency components, hence it functions as a high pass filter. And if you take the output across a capacitor, it functions as a low pass filter. And the real life example was a crossover network. Crossover network is simply an electronic filter that is used in speaker applications. Okay, it could be two-way speakers or two-way crossover network, or it could be for a three-way speaker, so it would be a three-way crossover network. Now, what happens at resonance? Well, at resonance, and resonance occurs at one single frequency, okay, not for any other frequency. At one particular single frequency, the impedance of the inductor and the capacitor are exactly the same in magnitude, but opposite in phase. Okay. So at resonance, electrical resonance, ZL would be equal to ZC, or actually magnitude of ZL would be equal to magnitude of ZC. However, the phase for the inductor would be exactly 180 degrees out of phase. Okay. ZL and ZC are out of phase by 180 degrees. This is similar to the example of noise cancellation technology. Remember what I stated as used as an example. If you have a time varying signal and you add it to another time varying signal that has the exact same amplitude and exact same frequency, meaning VM is equal, let's see, VM here is equal to VM here, frequency is equal to the frequency here, but the phase is 180 degrees out of phase. Then the result is 0. The result is 0. So in the same manner, if you add up the impedance of the inductor and the impedance of a capacitor, even though the magnitudes are the same, we do not expect 2 times ZL or 2 times ZC. The impedance of this will turn out to be 0. Because they are complex quantities, and because they are complex quantities, mathematically, we can show that they will go to 0. Okay, let's take a pause while you think on that. Let me know if you have any questions. And then after that, I will explain qualitatively what happens. Any questions at all? Okay, so then let's talk about what exactly is happening. Okay, and again, of course, we're not going too in depth, but this is an important concept because this actually is also applied for the next topic, which is AC power. Okay, AC power. So let's see. Inductors and capacitors are both energy storage devices. When you apply a voltage or current to an inductor or capacitor, energy flows into these components. Now, because it's AC, and you apply, if you apply a AC signal in the positive half cycle, so half cycle is HC, In the positive half cycle, energy flows into the inductor, okay? Into the inductor. In the negative half cycle, the energy flows out of the inductor. Capacitor is exactly the opposite. In a capacitor, a positive half cycle flows out of the capacitor. So let me see, out of, let's not do it this way. Positive half cycle out of the capacitor, and negative half cycle, it flows into the capacitor. Remember I said inductors and capacitors are very similar devices. They're exactly this, their behavior is exactly the same for many systems, but it's also the opposite in many ways. And the opposite is due to the energy storage capacities. So for inductor, positive half cycle, energy flows in. Capacitor, it actually flows out. So when you have both of these elements connected in a circuit, actually, let's take the case for when only one is connected. So if it's just RL or RC, if it's just RL or RC, what happens? In one half cycle, energy flows in and flows out, right? Energy flows in and flows out. So if it's just an inductor or just a capacitor, energy is continuously being transferred. In an ideal system, it would be 100% efficient. There would be no energy loss. But in real life, of course, there's energy loss that is taking place. So energy is constantly flowing in and out. But let's say you have both the inductor and the capacitor in the same circuit. What happens then? Well, when the energy flows into the inductor, and then when energy flows out of the inductor, so let's say when the switch is first flipped on, the voltage supply is connected to the circuit. The first positive half cycle, the energy will flow into the inductor. The entire system is at zero. Okay, there's no energy that is stored. Positive half cycle, the first positive half cycle, energy flows into the inductor, it gets fully charged. Negative half cycle, energy flows out. Now, if there was no capacitor present, the energy would go to the resistor, be dissipated, or go to the other parts of the circuit. But if there is a capacitor present, the energy flows out of the inductor. Instead of saying flows out, goes out of the inductor and into the capacitor. Okay, so the energy flows out of the inductor and into the capacitor. This is a very simplistic way of explaining the bare essential of that, bare functioning of that circuit. Okay, if you have an inductor and a capacitor together in a circuit and you apply an AC voltage or AC current, the energy that is coming from the source flows into the inductor first. When it comes out of the inductor in the negative half cycle, it goes into the capacitor. The capacitor starts storing the energy. In the negative half cycle, now when the energy goes out of the capacitor, in the next positive half cycle, when the energy goes out of the capacitor, it now goes into the inductor. So there's an energy transfer taking place between the inductor and the capacitor constantly. So let's take a pause right now while you think on that scenario. Okay. Let's say you had a signal of like 1 hertz, meaning 1 cycle per second. So every second in a positive half cycle, the energy flows into the inductor. The next half cycle, energy flows out of the inductor, goes into the capacitor. And the next positive half cycle, it goes out of the capacitor, back into the inductor, and then back and forth. So every half second, The energy is being transferred back and forth between the two, like a tennis match. Okay. The energy is like a ball that is bouncing between two ends, between two players on either side of the net. So energy exchange is being taken place. Think on that. Let me know if you have any questions. Any questions from anyone? Okay. All right. Then you're all with me so far, right? The energy is bouncing between the inductor and the capacitor. Now, depending on the frequency, depending on the resistors, depending on the entire circuit, depending on the, and specifically depending on the values of the inductor or the capacitor, this energy transfer is not equal. Meaning if the inductor is higher than the capacitor, then the inductor is storing a whole lot more energy than the capacitor can. Or the capacitor is much larger than the inductor, then it can store a lot more energy than the inductor can. Make sense, right? But the size of the inductor and the capacitor does not matter when at one single particular frequency, the energy transferred between the two is exactly the same. Okay, it is exactly the same. And that happens at a frequency that is known as the resonant frequency. So at resonant frequency, which is noted by F0, the energy transfer is completely balanced. Okay, energy transfer is balanced, meaning the capacitor and inductor do not require any further energy from the source. And this is the most important point. When the energy transfer, the ball that is bouncing between the two players in a tennis game, that energy that is being transferred between the two is exactly the same. Remember, the source is still connected. When the energy is exactly the same between the inductor and the capacitor, it does not pull any more energy from the source. So in mathematical terms, we say that the impedance of the inductor and the capacitor cancel each other out because it is not pulling any more energy from the source. It pulls energy when the switch is first flipped on, but because it can store energy, and this time when the energy is sent back into the circuit, there is another component that receives the energy. So it's not being wasted. So now the energy is stored within the system itself, and the energy is bouncing back and forth between the two components. The source does not need to send any more energy. So the maximum energy from the source is going to the third component in the circuit, which is the resistor. And so output at resonant frequency across the resistor goes to maximum. Okay, output across that resistor goes to maximum. For all other frequencies, either the inductor or the capacitor is going to pull a little bit of energy from the source. So the output across the resistor, excuse me, sorry. So the output across the resistor is always lower than that maximum. Mathematically, we can explain it by saying the impedance ZEQ of the entire circuit is slightly higher than R. And I'll explain the mathematical equation in the next few minutes. But does the qualitative explanation make sense? Okay, for a series resonant circuit, we take the output across the resistor. at one single particular frequency, the energy transfer between the inductor and the capacitor is exactly equal. It's balanced. And so output across the resistor goes to maximum. For all other frequencies, output is less than the maximum. And then we obtain a graph or a chart that looks like this. Where is my image? There it is. So here we say that the output is max. This is, of course, a chart of frequency. Sorry, not frequency. We would say transfer function h of f as a function of frequency f. You could also say this is V out. V out as a function of frequency. Okay. We normalize it because all systems do not have the same voltages. So if you want to compare multiple systems together, then we normalize it. Because some systems might have millivolts as the input, some systems might have like volts or tens of volts or hundreds of volts. So if you want to compare one system to another, we normalize everything. So if you normalize it, everything has a max value of 1. Ideal system, of course, max value at F0 would be 1. So this is the max value. And max value is only obtained at the resonant frequency, which is F0. For all other frequencies, the output drops. Okay, output drops. Because for all other frequencies, either the inductor or the capacitor requires a bit of energy from the source. And so if you're taking the output across the resistor, the output would be less. And when you plot these characteristics, we can see that these characteristics are for a band pass filter. There is a certain band of frequencies in the middle that is allowed to pass through. All the frequencies are blocked. So let's take a 10-second pause. Think on that. Let me know if you have any questions. Any questions? Okay, so mathematically, let me show you what happens with the impedance. What is the ZEQ of the circuit, the total equivalent impedance of the circuit? It's in series. 3 impedances in series add up exactly the same way as resistors in series. And so ZEQ is simply R plus ZL plus ZC. But at resonant frequency, F0, not FO, F0, ZL plus ZC goes to 0. And therefore, total ZEQ is simply equal to the resistor R. That's the lowest equivalent impedance in the circuit, and hence the output goes to maximum. And of course, this is the mathematical explanation, right? Voltage from Ohm's law, voltage is equal to I times Z, right? I times Z, V equals IZ. So current goes to maximum, and the maximum voltage appears across that resistor. Make sense? Right? Now, let's take a pause. Let me know if you have any questions. Okay, so then what happens if we connect these in parallel? We had series connection, but what happens if you connect all three of them in parallel? You still have a RLC circuit. The fundamental concept still remains the same. You have a source that is now supplying voltage or current. You have an inductor and a capacitor and a resistor in that circuit. Energy transfer or exchange takes place between the inductor and the capacitor. At one particular frequency, the energy transfer between the inductor and capacitor is exactly the same, and that happens at resonance. So it's the same explanation at F0. The impedance of the inductor and the capacitor are exactly the same, but opposite in magnitude. So ZL plus ZC goes to 0. Energy transfer between the two is exactly the same. And so at resonant frequency, neither the inductor nor the capacitor pull any energy from the source. So the resistor gets all of that energy. Okay, so the qualitative explanation is exactly the same. There's no difference. But because of the parallel connection, if I try to mathematically add up the impedances of the inductor and capacitor, what do we obtain? ZLC would be 1 over ZL plus 1 over ZC. And then if we solve this, what do we get? 1 over, this is the sum of the two, product of the two divided by the sum of the two. So you got ZL times ZC divided by ZL plus ZC. And so we get 1 over ZL times ZC over 0. And so 1 over ZL plus 1 over ZC goes to infinity. Actually, let's see. Just the parallel combination of this. Yeah. And so this will tend towards infinity. Because this will also be added up. So ZEQ would be equal to 1 R plus 1 over R plus 1 over ZLC, which would tend towards infinity. So if ZLC tends towards infinity, it will not pull any energy from the source. The only thing left in the circuit would be similar to the previous situation in series circuit, which is the resistor R. Output goes to the maximum because all of the energy from the source is flowing through the resistor, and V out goes to maximum. So at F0, V out goes to maximum. And then yet again, if we plot, we obtain the exact same plot for a parallel resonant circuit, where the output goes to max at F0. Maximum output. Okay, maximum output. I'm going to show these together because the equations and everything are pretty much the same for both. Okay. So let's go back to the series resonance and I'll show you the equation. So that one single frequency, which is the resonant frequency, is dependent on the values of the inductor and the capacitor, and is given by F0 is equal to 1/2 pi root of LC. 1/2 pi root of LC. This is true for both series as well as parallel. Okay. In terms of omega, omega is 2 pi f. So omega 0 is simply 1/root of LC. The resonant frequency depends on the physical values of the inductor and the capacitor. Okay, depending on the frequency, the energy transfer that is taking place becomes balanced at that single frequency. Then we define two other terms, FL and FH. And I'll take a pause for a few seconds, and then we'll talk about those. Okay. All right. So let's go back here. Remember what I said. A band pass filter, series resonance circuit can function as a band pass filter. However, if we take the output across the inductor, we have a high pass filter. If we take the output across the capacitor, we have the low pass filtering option, or the low pass filter. So it is a combination of two filters connected together, right? That means if you take the characteristic of a low pass and a high pass filter together, and you combine them, you get a band pass filter. So this is the low pass filter characteristic. This is the high pass filter characteristic. And each one of them would have a break frequency or a cutoff frequency. This would be FB for high pass. This would be FB for low pass. If you combine these together, you get this band of frequencies that is allowed to pass through. And this is known as the bandwidth B. Bandwidth B, which is shown in this equation right here. Okay, FH minus FL. Now, the L and H that are noted in the figure here simply refer to the values of the frequency on the x-axis. Pure values. They are not indicating a low pass or a high pass. The L and H simply refer to the values. Because it is 0 here, then the first value to come is noted as FL, and the second value to arrive is FH. That is it. It's just pure values. It doesn't mean anything else beyond that. If you read a different book written by a different author, if you take a different class, they might refer it to as FB1, FB2, might interchange FL and FH. But in this case, in this book and in this class, the L and H simply refer to the values, numerical values. It doesn't signify anything else. Okay. Sometimes it's just referred to as F1 and F2. But in any case, the difference between the two frequencies is defined as the bandwidth of the circuit. It is defined as the bandwidth of this band pass filter. In real life, we want the bandwidth to be as narrow as possible. Think of your, as a real life example, think of your AM radio stations or an FM radio stations. If you're driving down the road, if you're driving in the highways, sometimes if you have tuned into a radio station, you might get interference from a different station coming at the same time. And the reason is, let's say one station is broadcasting at 107.1. The next station might be broadcasting at 107.3. Seems like it's close together. So if you're tuning, if your radio is tuned to a frequency right in the middle, it is going to receive signals from both radio stations at the same time. Okay. And that's why you might hear two different voices coming from two different radio stations at the same time. Has anybody ever encountered such a situation? Ever? And that's what is happening. It's interfering. So when you design a filter, you want that filter to be very narrow. If it's 107.1, you want that band pass filter to only allow 107.1 megahertz signal to go through. Obviously, in real life, you can never make a band that looks this narrow. So again, as I stated, filter design is a real, it's very hard. It's a specialized topic within electrical engineering. Like filter design is of crucial importance, and this is the reason why. Frequencies, everything in this world runs on frequencies, all electronic devices, all electronic communication. If you have interference, it doesn't work. Which, as a public service announcement, I will segue a little bit into what criminals do nowadays. Used to be that if you have a residential or commercial security system, it would all be wired, right? You would have installers come out, they would wire up your entire place, and you'd have wires running all around and connected to your phone lines. If somebody breaks in, it trips the wires, it trips the sensors, and the phone lines would send a call, distress signal to the appropriate authorities. With the advent of wireless, everything is now Wi-Fi. Everything is connected towards wireless. But as I just stated, everything that runs on wireless, if you broadcast a signal at the exact same frequency, it is now causing interference. And so you might have heard of Wi-Fi jammers, perhaps. And Wi-Fi jammers are nothing but broadcasting devices that broadcast at the exact same frequency as our wireless routers. So if your wireless router is running at 2.4 gigahertz or 5 gigahertz, and you set up a signal in the exact same vicinity as your Wi-Fi router and your devices are now confused. Instead of connecting to the wireless router, your wireless cameras are now connecting to that Wi-Fi jammer. And so it's not capturing any signal, or if it's capturing a signal, it's not going to the router itself, it's going to the Wi-Fi jammer. And so wireless is very convenient for our end users, but it's also very convenient for criminals. It's very easy for any criminal to hack into a system because they don't actually need to do any hacking. They can just take a Wi-Fi jammer, broadcast at the same frequency, and just jam up the airwaves. So again, public service announcement. If you're ever in the situation, it's a bit of general knowledge. All right, let's take a pause. Let me know if you have any questions about this. Any questions? Okay. All right, so as I was saying, what you'd want is, as an example, if it's 107.1 megahertz, we want a filter that would be as narrow as possible. Ideally, we would only want it to pass that one single frequency and block everything else. Real life, it's not possible. So that one particular frequency is passed, as is some other frequencies on either side are allowed to pass. But we want that band to be as narrow as possible. So we want the B to be as low as possible. And we define a term known as the quality of that filter circuit. This quality Q is not the same as the quality of the inductor or quality of the capacitor. This is the quality of the filter circuit. Okay, this is the quality of the circuit to function as a filter. Okay, if you see, it is F0 divided by B, meaning the bandwidth around the resonant frequency. Ideal filters, that bandwidth would be equal to 0. Right? If it's allowing only a single frequency to pass through, then FL is equal to FH, meaning the bandwidth is equal to 0. Quality is infinite. Real life, not such a case. You know, it's not possible. So as long as it's very narrow, we'll have a very high quality. And if Q is much, much larger than, let's say, 10, then we can say the characteristic we assume the characteristic is symmetrical. Oh. Symmetrical around F0, meaning FL and FH are exactly equidistant from F0 on either side. Okay, they are equidistant from F0. And so we can then state FH is equal to F0 plus half the bandwidth, and FL, which is on the left side, is exactly equal to F0 minus half the bandwidth. And again, these are equations. You don't have to memorize these equations, obviously, as long as you first understand them. Okay. The S, the subscript S, notes that it is a series resonance circuit. Hence, it is QS. When we get to the parallel circuit, the definitions are exactly the same, but the subscript is QP. QP. Okay. QS and QP can also be given in terms of the components, and those equations are right here. Oftentimes, again, as I said, students don't have to memorize these. Oftentimes, even I can simply not remember from the top of my head. With so many equations in your own fields of engineering, I absolutely understand. Okay. All right, so that is or concludes resonant circuits. Let's take a longer pause. Let me know if you have any questions. Any questions at all? All good? Okay, then I just want to talk a bit about Bode plots. Let's see. Yes, those magnitudes, Bode plots. Okay, so in engineering, pretty much any scientific field, we are required to deal with very large values and very small values. Okay, so this was a problem that was very typical during the early days of telephony. You're transmitting a signal from one end to another, from point A to point B over very long distances. So there would be a loss of signal, there'll be a loss of power during the transmission. So when you sent a normal signal from one end, is going to travel over tens of miles, reach the far end, and you'd be measuring the signal in probably milliwatts or millivolts. Okay, so engineers who are working with very large frequencies and very small magnitudes of voltages and power. So they had a frequent problem of trying to actually plot these on a single chart. Okay, so at that time there was, computers just recently came about in terms of, well, when I say recently, it's just the last few decades, right? So previously everything was done by hand, manual calculations, manual plots. So H.W. Bode was an engineer who was working for, I believe, Bell Labs. And he came up with a unique way to graphically plot the transfer function of a circuit, filter circuits, with respect to its frequencies. And what we do in these is that it plots the magnitude and frequency both in a compressed form. Okay, both in a compressed form. And so you could then approximate the filter characteristics by using straight line asymptotes. Asymptotes are a term that is tangential to your curve, but never quite touching it. So it's straight line approximations. And what we do is we compress the frequencies by using the log scale. And then we compress the output of our filter circuits, again, using a new term based on the log scale. So the first up is frequencies. When you take the log of two frequencies to the base 10, you get what is known as a decade. Decade of frequencies is basically a 1:10 change from one frequency to the next. So let's say if you're talking about frequency 1, which is 10 hertz, and frequency 2, which is 100 hertz, that is a ratio of 10, and that qualifies as 1 decade. 20 to 200 is the same, and so is 50 to 500. If you go from 10 to 1000, that is a ratio of, and so if you take log of 100, it's a change of 2. So this qualifies or signifies that it is 2 decades of frequencies. You're compressing your x-axis by taking the frequencies and plotting it on the log scale. Okay, not linear. Linear scales, you add, right? So it's 0 plus 1 plus 1 plus 1 plus 1. So it's 0, 1, 2, 3, 4, 5, 6. In a log scale, it is 0, 1, 10, 20, 30, and so on and so forth. Octaves is exactly the same thing. We won't encounter anything known as octave. But if you take any two frequencies to the log of 2, then the difference between the two frequencies is defined as 1 octave. 1 octave. Okay. So again, example here is between 500 and 1000. It's a 2 to 1 change between any two frequencies. So 10 to 20 or 20 to 40, 100 to 200, 2 to 1 change is basically 1 octave. It's basically plotting the frequency on log chart. How many of you have seen this before or used this before? As engineers, you may use this or you may come across its usage in your own fields. This is known as a semi-log graph or a semi-log chart. It's known as a semi-log because only one axis is in the log scale, the other axis is in the linear scale. Okay, it's a log scale because the physical distance between two divisions is the log of the difference. Okay, so if you start from 1, the next division is 0.3 of the large division apart, meaning log of 2 signifies or notes where the next division occurs. And then so on and so forth. Log of 3, log of 4, so on and so forth. Okay, so every division in here is spaced apart exactly by its logarithmic definition. In a log scale, there is no 0. We start with 1, which makes sense. The way it works, and I'll quickly explain this, is that the linear scale is a summation. It's an addition. Log scale is a multiplier. Okay, and I'll show you right now how. So for the first division, starting from here to here, you note that the divisions start from 1. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9. And then it again starts from 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then again starts from 1, 2, 3, 4, 5, 6, 7, 8, 9. Now it's showing here 10, but I'll show you how and why. So let's say the first multiplier is 10 raised to 0. The second multiplier is 10 raised to 1. Third one is 10 raised to 2, 10 raised to 3, and 10 raised to 4. So if you start from the first, this is 1 hertz. So 1 into 10 raised to 0 goes all the way up to 10 hertz, 100 hertz, because the first one is 1, then it goes 2, 3, 4, 5 until 10. And then the multiplier changes. So 2 into 10 raised to 1 becomes 20, 30, 40 until you reach 100. Then 100 goes to 200, 300, 400, and so on and so forth until you reach 1,000, then 10,000, and then 100,000. So you went all the way from 1 hertz to 100,000 hertz. On a linear scale, you would need a paper that is about a mile long. Just a wild guess. But does this make sense? All right, let's take a pause. Let me know if you have any questions. Any questions? Okay, so let's look at what happens to the y-axis. So this was, early days of telephony. Engineers were working with trying to quantify power loss that occurred in transmission lines. And so they had to come up with they came up with a new unit to actually, quantify this, ratio of powers. And it was named after anybody? Anybody? Telephony, Bell. Does that ring a bell? Excuse my poor puns. Alexander Graham Bell. Who else? So the ratio of 2 powers, the log of 10, was given the unit of 1 bell, or B. This B is not the bandwidth, uppercase B. It signifies the unit for the ratio of powers. If it's the ratio of powers, obviously it's unitless, it's dimensionless. So they came up with a new term to describe it, right? Bell. And 1 bell is equal to 10 decibels, which nowadays you might more commonly as its short form or acronym dB. dB. So 1 dB is technically given by 10 times log of the ratio of the 2 powers. So if you have power being transmitted, let's say P1 and P2, and you want to quantify that loss, because at one end you might be transmitting like 1 watt or 2 watts or even tens of watts, and the other end you might be receiving, let's say, milliwatts. That's a wide range. So it's a wide difference between the two ratios, and because it's a wide range, well, you use a new unit. Now if you think about this unit, it is again a log scale. Remember the previous chart where I said x-axis is log, y-axis is linear. It's linear, but it is still compressed. And it's compressed before you plot it. So that's the big difference. The x-axis is compressed right here, plotted on the log scale. And the y-axis, you are plotting linearly, but the values are compressed itself. And because the values are compressed, you can plot a very wide range of units on the same small chart. Now, Bode plots, what they did was, if you take a look here, power, what is the equation for power? Power is V squared over R. So when you take the log, what happens? 2 times 10. 2 times 10 equal to 20. So if you take the ratio of voltages and you take the ratio of powers, that's what happens. For a circuit or a filter circuit, we talk in terms of V in and V out. So if you take the ratio of powers, it is 10 log. When you take the ratio of voltages, it is 20 log. And we use ratio of voltages because we want to describe in terms of the transfer function. So transfer function, which is a ratio of voltages, is unitless. There are no units. If you plot those in the decibel scale, then h of f in dB is 20 log of h of f, the magnitude of h of f. All right, let's take a pause. Let me know if you have any questions. Does that make sense? So both axes are compressed. And then we get the plot. All right, let's look at the last slide before we take a short break. So Bode plots basically exist for both magnitude and phase. We use straight line approximations to plot. So if this, I'm going to draw without the axes. If this is a low pass filter, this would be where the break frequency occurs. And so, not good. Let's see. So this, for a low pass filter, would be the low frequency asymptote. Right there. And this would be the high frequency asymptote. Okay. For a high pass filter, it'd be the exact opposite. High pass filter would go something like this. And so if you had this would be the high frequency asymptote, and this would be the low frequency. This is, of course, a high pass filter. So you can use straight line approximations to quickly plot out Bode plots and frequency response of filter circuits. All right. Let me know if you have any questions. Otherwise, we'll go take a short break before we get to AC power. You will stop recording.